All right, ladies and gentlemen, here we are. We're in Dr. Rogers' neighborhood. We have Doctor Who behind us. And what we'd like to do is finish up the lecture that we started last Monday. Now, you know, we got as far as normal distribution. We said that was a continuous probability. As you can see on the screen, you know, this is a two-tailed t-test. In other words, there's 50% under the one side of the mean and 50% to the other side of the mean. And so the area under this normal curve will represent 1. And you have to use the Appendix A in the back of your book to find the number of standard deviations that correspond to the probability of this occurring. Well, after a little bit of a pause there. At any rate, let's take a look at, you know, at the formula here. Again, z is equal to x minus mu over the standard deviation. And, you know, in this example, we have a mean of 4,200 yards that someone sells and a standard deviation of 1,400 yards. Now, what's the probability of a salesperson selling 6,000 yards? Well, you know, 4,200 is the average, so probably that percentage is not going to be very much. That's probably over 1 standard deviation above the mean. So again, the mu, or the mean, is 4,200 yards. The standard deviation is 1,400. We want to know the probability that the number of yards of carpet would be equal to or greater than 6,000. And this is, again, expressed as the probability that x is greater than 6,000. So here's the area under the curve that we're looking at. You can see here in the middle that the mu is 4,200. The standard deviation, plus or minus, is 1,400. And here we want to know 6,000 yards. Well, look here. 4,000 plus 1 is 5,600. This 6,000 is way above 1 standard deviation. So let's again see what what the results are. Here's our formula. The area probability under a normal curve is measured by determining the number of standard deviations, is right here. The value of a random variable x that we want to take a look at, in this case it's 6,000, from the mean, which is 4,200. What is the number of standard deviations from the mean? That is designated as the z term. So here again, we know that in a normal distribution, 68% of the population is going to fall within plus or minus 1 standard deviation. 95% within plus or minus 2 standard deviations. 98% within plus or 3 standard deviations. Now, if we go and we run this through our processor here, and we say that z is equal to x minus mu over the standard deviation, 6,000 minus 4,200 over 1,400, we come up with 1.29 standard deviations. We have to go to the back of our book, to Appendix A, and that is, comes out to 40.15%. Now again, it's a two-tailed t-test here. There's 2 sides to the distribution, and so we want to know here, here's the whole thing is 0.5. 1.29 is not included on that because, that's up to the 6,000. It's the 6,000 and above we want to look at. So if we subtract the 0.4015 from the 0.500, we will come up with about a 10% or 0.0985% chance that someone or a salesperson will sell more than 6,000 yards of carpet. So again, we could come up with another example here. And what is the probability that it will be less than 5,000 yards? Well, if you use your logic, again, that's going to be a lot easier because 4,200 is the average. So, less than 4,200 is the mean, and this is this area in here. So that includes all of that. Now they're also going to sell another above the 4,200. So 5,000 minus the 4,200 divided by the standard deviation is only 0.57 standard deviations, about half of a standard deviation. So this area under the curve plus this from the mean of 4,200 up to the 5,000 yards right here has to be added on. If you go back and you look at 0.57 in the back of the book, and you will see that it comes out to a probability of 21.57% or 0.2157. You add this on to the 0.500, this side of the bell-shaped curve, you will come up that there's a 71.57% chance that someone will sell 5,000 yards of carpet or less. And here again, since we already figured out what the 5,000 was, all we'd have to do is figure out now, we want to know between 3,000 and 5,000. We know what the 5,000 is, and that came up to 21.57. If we go through our formula again here, we will find out that the 3,000 comes out to 30.51%, and the total of between 3,000 and 5,000 yards is 52.05% in the normal distribution. So again, maybe a few words here about population versus sample, as we talked about in class. A census or a universe is everything. Everything is looked at. The population is a smaller component of that, and then the sample is a subset of the population. So, the universe in the state system of higher education may be all students within the state system of higher education. The population we may look at is the student population for IUP, and the sample may be the graduate students at the North Point EMBA program, and take a look at their grades and how they compare to the population and to the census of the normal distribution. Here again, the sample mean is simply the average. X bar is equal to the summation of the sample number initialized with the first one and continuing on through. The sample variance is the standard deviation squared, and the standard deviation is the square root of the sample variance. So here again, if we go through, we can do this the long way. Again, if to come up with this 190,060,000, we would have to go through the previous formula here and calculate that out. Now again, the other number, the 1,764,000,000, is a fairly easy number because that's simply 42,000, and that is squared will give us this number. So we go through here and we will find out what the sample variance is 1,517,777. Standard deviation is the square root of that and is 1,232 yards. Yeah, so again, we can't always assume that something is normally distributed. So if it is not normally distributed, we cannot use this parametric type of methodology. We can't use ANOVA. We cannot use regression. We have to use chi-square. Now, chi-square also has a goodness of fit, much like the normal distribution. Regression has a goodness of fit, which is r squared. And again, if we take the actual number of frequencies and we compare that to the theoretical frequencies, so we take what actually occurs and then we compare that to the observed, and we will come up with this thing called a critical value, just like you have a critical value for the t-test at the back of the book. So if the t-test statistic is greater than the critical value, then the distribution does not follow. It's in the distribution being tested. If it's less, then the distribution fits. So this tells us whether it is normally distributed or it is not normally distributed. And again, we can use this as a hypothesis testing. So here again is another example. We can go through this with the 4,200 yards, take a look at the standard deviation. We can see whether or not we have go through this calculation, see whether we have a normal distribution. We take a look at the observed frequency, the theoretical frequency. Again, K is the number of classes, P is the number of estimated parameters that we have, and K minus P minus 1 is the number of degrees of freedom. So we have another, in the back of the book, we have another table, and we have to use that table for the chi-square. So if we add this up here, we will see, we'll go through all these calculations, and now this is the observed, this is the theoretical, this is taking the theoretical from the observed and squaring it, and then dividing it by the theoretical, and we will come up with 2.588. Now, again, what's going on? If we look at this in the back of the book, and we have to look at the 2.588 with 3 degrees of freedom, and we're going to say the level of confidence is 0.05, meaning that there's a 95% chance that there is a relationship here, but there's still a 5% chance that it is due to random chance alone. And we go to table A.2, we look up the chi-square of a 0.05 level of significance with a degree of confidence and 3 degrees of freedom, and that value is 7.815, because that value, 7.815, is greater than the value we came up with, 2.588. We will accept the hypothesis that this is a normal distribution. If the opposite was true, if 2.588 was greater than that critical value, then it would not be normally distributed. So again, this can be done in Excel. We can do the statistical analysis there. This shows us how we'll do it. And here again is another example utilizing the number of accidents and whether or not a company should, whether you should buy accident insurance or not, and what it would cost you in a 1-year period, what we would expect to pay. So here again, you've got accidents here that are less than 5 and accidents that are more, 10. We want to take a look at that. The mu is equal to 8.3 accidents. The standard deviation is 1.8. So again, what we're going to do is take a look at less than 5, and then we're going to take a look at greater than 10 accidents. If we look at less than 5, now this is going to be where? On the left-hand side of the normal distribution. Z is equal to x minus mu over the standard deviation. 5 accidents minus the average of 8.3, or mu, over 1.8, gives us a negative 1.83. It's on the left-hand side, below the mean. And we take this, look this negative 1.83 up, and it gives us a 0.4664 probability, and you have to subtract that from the 0.5, and there's only a 3% chance about that you will have a less than 5 accidents. Now, if we look at it from the other direction, and we look at it from 10 accidents, 10 minus 8.3 over 1.8, and standard deviation is 0.94. Take a look in the back of the book. There, the probability is 32.64%, and P is equal to 0.5 minus 32. There's only a 17% chance that you'll even have as many as 10 accidents. So, is insurance worthwhile? What is the probability of having 12 accidents? Well, Z is equal to 2.06. That's 2 standard deviations above the mean, and that has a probability of 48%. So 0.5 minus the 48% is only a 1.97% chance. So take that times the $200,000, and you would expect to pay $3,940. Thank you, class. I hope that I was able to answer your question.